Now, neutralization reactions are those between acids in solution and bases in solution. And you probably remember that acids are substances that produce the H+ ion in aqueous solution, like nitric acid, hydrochloric acid, and so forth. If you dissolve those substances in water, you get a solution which will light the light. Nitric acid lights the conductivity light very nicely because it dissociates almost completely into ions. There are many bases also that will light the light in their solutions, and in general the bases produce hydroxide ion in water, either by dissociating hydroxide ion directly or reacting with water to give hydroxide ion. As a rule, acids and bases may be strong, medium, or weak in terms of their electrolyte behavior. And they are typically, for simplicity, recognized as strong acids or weak acids. The strong ones being the one that dissociate completely in solution. And table 4.2 shows you the strong acids that we want you to learn: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. These are binary acids, 2 hydrogen and 1 other type of atom present, and these are these are acids based on polyoxo anions, or just oxo anions. All of these are strong, meaning that if you dissolve them in water, they dissociate essentially completely to H+ and Cl-. Yes, go ahead. Memorize those, yes. These strong ones and these weak ones, and this is one that pops up on tests all the time and many students miss it. HF, hydrofluoric acid. Many students think that because hydrochloric, hydrobromic, and hydroiodic acids are strong acids, hydrofluoric acid must be too. It's not. It's weak. Okay? Phosphoric acid is also a weak acid, and acetic acid is too. We saw a solution of acetic acid in the conductivity apparatus, and it lit the light, but it was very dim. So, the first part of 4.2, please memorize those. Strong acids and strong bases then dissociate fully, so they're strong electrolytes. Weak acids and bases dissociate much less, and that means that mostly the molecules of the acids and the molecules of the bases remain intact if they're weak. Only a few of them actually dissociate that way. The list of bases is much smaller. We have only 5 strong bases that we expect you to learn: sodium hydroxide, potassium hydroxide, and calcium, strontium, and barium hydroxide. Those are all strong acids and strong electrolytes. And there's only 1 weak acid that we expect you, weak base that we expect you to learn. That's ammonia. Okay, so memorize those things as well. Now, strong bases, in some cases, are not hydroxides. All of these strong bases are hydroxide, but it's possible to have a strong base that's not a hydroxide. And an example of that is an ionic oxide, like barium oxide, solid. If you add it to water solution, you have the oxide ion reacting with the water to give hydroxide. And barium hydroxide is one of the strong bases that we wanted you to learn. So if you run into oxides like this, you can expect them, if they're soluble, to react with water and make hydroxide ion. The weak base ammonia does not contain either the oxide ion or the hydroxide ion, but it does react with water to produce a little bit of hydroxide ion. This is not really very much. We write the equation like this, and this is sometimes referred to this solution as ammonia water. And it's the stuff that you might use as a cleaning agent or as one component of a cleaning agent. Under the sink, ammonia water. What you should recognize here is even though the equation says you get hydroxide here, you get only a few % of the available hydroxide functionality associated as hydroxide ion. So ammonia is really quite a weak base. Okay, now I want you to look at the reaction between a strong acid, hydrochloric acid, and a strong base, barium hydroxide here. When these two solutions are added together, and the amount of each one of them is right, in other words, the ratio of the number of moles of hydrochloric acid compared to the number of moles of barium hydroxide is 2 to 1. If you have that ratio, then you will get a complete neutralization. Strong acid reacts and neutralizes a strong base, and you will get a salt, barium chloride, plus water. So you frequently see the statement that neutralization reactions of strong acids and strong bases produce a salt and water. The cation of the salt is contributed by the base. The barium hydroxide contributes the barium of the barium chloride. This is the salt. And the anion of the salt comes from the acid. Now, both of these substances are strong electrolytes. So if we wanted to write the total ionic equation, we've written the molecular equation up here. The total ionic equation be arrived at by dissociating HCl to H plus and Cl minus, dissociating barium hydroxide to barium 2 plus and 2OH minus, and so forth. So this is what we would have for the total ionic equation. 2H plus plus 2Cl minus, that's the 2HCl, plus barium 2 plus and 2OH minus, that's the barium hydroxide, aqueous. And then on this side, the barium ion and the chloride ion come respectively from the base and the acid, and the water, indicated in blue here, comes from the 2H plus and the 2OH minus. So does this qualify as an ionic reaction? What do you think? What must be true if it's to be counted as an ionic reaction? Ions must be what? Come on. Removed. Ions must be removed from solution, right? Don't be shy. Are ions removed from solution? You bet. 2H plus and 2OH minus go to form water. So this qualifies as an ionic reaction, and in this particular case, the two ions go to form the neutral compound water. So that's where the ions go. And if we were to ask what are the spectator ions, the answer would have to be the barium, the chloride are the spectator ions. So if you had to write the net ionic equation, you would get busy and take the spectator ions out of there, and then what you would have left is 2H plus 2OH minus goes to 2H2O, and if you wanted to put that in the proper form, you would divide through by 2, and it would be H plus OH minus goes to water. That's the net ionic equation, and that's what happens in this reaction. Does anyone have a question about neutralization? Yes, go ahead. What's the difference between the, I couldn't get the last part. This L right here. We write that L because that we recognize that water is a liquid under normal circumstances. If you wrote AQ here, that wouldn't be wrong, really. because water is dissolved in water. The water that's formed is just dissolved in the water that's there. So it could be done either way, but the usual conventionality of it is to put an L there for the water. Other questions here? All right. Now, how do you carry out neutralization reactions? Well, if you have the concentration of the acid and the base, you can just use the usual rules and figure out how many moles of base and how many moles of acid you want to react, put them in the right ratio, and just put them together and stand back. But frequently in the laboratory, we encounter a situation where we don't know the concentration of both of those. Maybe we know the concentration of the base, but not the acid, or vice versa. And when that's the case, usually what we have to do is to carry out what's called a titration, which is nothing more than a neutralization reaction carried out quantitatively. And what usually happens, or one possibility, is that a standardized base solution, meaning one whose concentration we know, is slowly added drop by drop to an acid solution of unknown concentration. And in order to find out when the reaction is done, when all the H plus and OH minus have combined, we use an indicator which changes color when the hydrogen ion concentration of the solution changes. So we might start out with a situation like this. We have a burette which has a graduated tube on top that shows the volume. It has a valve on the bottom and a flask here that might have the acid in it. In this case, it would have the acid in it dissolved in some amount of water. And we know the volume of this solution, but we don't know its concentration. And in the burette up here is the base solution, and we know its concentration, and we use the burette to figure out what volume it takes. So a known volume of acid is placed in the flask with some of that indicator solution that I mentioned. It's going to change color when we get to the end of the reaction and the neutralization is finished. So the base solution then is added slowly from the burette clamped above the flask. And you stir the flask, you swirl it, or you take a glass rod, continue to agitate the solution a little bit, stir it up to be sure that any reaction that could occur has occurred. You keep doing that and watch the solution. After you get a ways into this and you've added some of the base, you add a little bit more base, you see a color change which occurs and then disappears. In this case, it's the formation of a pink color. It stays there for a little bit, but then when you swirl it, it disappears. So that's your key to slow down. Start adding the base more slowly, drop by drop. Or you can go past the end point. And the end point occurs when the color just stays. And you should be able to get to that point by adding just one drop of solution, which means you've gone one drop past the place where the number of moles of base and the number of moles of acid were equivalent. At the equivalence point, the moles of H plus present in the flask is equal to the moles of hydroxide delivered by the burette. So typically what we will do is, knowing the volume of the acid and knowing the concentration of the base, we can measure the volume of the base, and from those three things we can calculate the fourth thing, which is the concentration of the acid. Here's our HCl and barium hydroxide solution again. That could be done by having an unknown, that could be treated by having an unknown hydrochloric acid solution in the flask and adding barium hydroxide slowly from the burette. Well, let's look at a particular problem. This problem hinges on us knowing how to calculate an unknown concentration from an acid-base reaction. Later we'll talk about redox titrations as well. This problem says 50 milliliters of hydrochloric acid is placed in a flask. 50 milliliters, that's the volume of the acid. A burette holds 0.1524 molar sodium hydroxide. That's said to be standardized sodium hydroxide. And the initial volume is 0.55 milliliters. Now, if you've ever done a titration, you know there are some people who will try their hardest to get the initial volume at 0, like it mattered. Okay? As long as it's on the graduated part of the tube, it doesn't matter, does it? So 0.55 is the starting point, and 33.87 is the point when the pink color shows up and just stays. What is the HCl concentration? First of all, we need a balanced chemical equation because we're going to have to do a mole-to-mole ratio here. And the mole-to-mole ratio is going to come from the coefficients of the balanced chemical equation. And then, fortunately, it's a simple one. Sodium hydroxide plus HCl goes to sodium chloride, the salt, plus water. Now, we have the volume of HCl, but we don't have the concentration. We have the concentration of sodium hydroxide, and now we have the volume. It'll be the difference between 33.87 at the end and 0.55 at the beginning. So we're going to use the volume of the base to calculate the moles of base. Because if we want the concentration of the acid, we need to have the moles of the acid and the volume. We got the volume, 50 milliliters. It had to be converted to liters, but we got the volume. So we need to know the moles of acid. So we're going to get the moles of base, and then we're going to do a mole-to-mole conversion to get the moles of acid. Okay, the volume of base in liters would be the difference between the final volume and the initial volume times 1 liter over 1,000 milliliters, and that's 33.32 milliliters, or 0.03332 liters. That's the first step. Questions on that? Okay. The second step is to use that volume and the concentration to get the number of moles of sodium hydroxide that is consumed. 0.03332 liters of solution times 0.1524 moles in 1 liter. The liters cancel, and we get 5.078 times 10 to the minus 3 moles of sodium hydroxide. Well, that's the first step. That's the end of the first step. Now we need to convert this to moles of acid and then get the concentration. So the balanced chemical equation showed 1 mole of HCl to 1 mole of sodium hydroxide. So this really changes nothing, but just for form, we're going through it here. 5 times 10 to the minus 3 moles of sodium hydroxide times 1 mole of HCl over 1 mole of sodium hydroxide, not surprisingly, gives 5 times 10 to the minus 3 moles of HCl. So that, you might think, well, why doesn't he just leave that out? That looks like he's just taking up time. Suppose it had been the barium hydroxide and HCl, okay? Then it would be 2 moles of HCl to 1 mole of barium hydroxide. And if you left it out, you'd get the wrong answer. And believe me, if it was on the exam and it was a multiple choice test, there would be one choice that was set up to trap people who left out that. So you don't want to get caught, right? You don't want to get caught. All right, then the last step is to calculate the concentration. Concentration is moles over liters. We have milliliters here, so we have to do a milliliters to liters conversion here. And the final answer is 0.1016 molar HCl.